So this is the second part of the introduction based on the active inference blog and paper, um, uh, which sort of tries to cover the concepts. Some of this a little mathematical. So I will, you know, remind what we had we have seen last week, and this is kind of the basic premise that uh, there is a tendency of the brain to model the world in a way that it will anticipate um, events. And, in this formulation, the anticipation is actually not in time. Anticipate means just basically learn the probability of things, how they might occur. And this, in some sense, the ability of the brain to adapt to the environment is referred as surprise avoidance. So the underlying model is that there is a world that generates observations, and there are some underlying causes for these observations, which are these states, and these are the true states uh, that the brain tries basically to learn, but they're masked in some sense, or they're not visible for us. So all we see are the sensory inputs, and the whole premise here is of Bayesian framework, where the states are random, the observations are random, and there is kind of a probability joint distribution. That is, all the relations within them are given by this Bayes rule. So you can either, given the causes, given the observations, you are able to judge the probability of the states, the underlying basically causes, or you can go the other way around. Given the states, you can guess the observations. So the brain is basically trying to learn the probability of the states, of these kind of hidden states. And the quality of the brain's ability to avoid surprise or adapt is measured by these two criteria, which amount to this free energy principle. So there are two ways to write this down. One is energy minus entropy, and that's where the name comes from. And it's a little kind of a borrowing from physics or thermodynamics. And there is no real entropy or energy in this formulation. It's all just probabilities of events. So it's not like you can put a thermometer and measure, temperature or heat. It doesn't do physical work, but it just uses the same kind of formulation. So we have to agree that these are just borrowed terms. So the energy corresponds basically to the quality of the approximation, or the quality of the ability to guess what's happening in the world based on whatever the brain learns, which is this probability of these hidden states. And the entropy is basically a measure of the amount of freedom, in some sense. In that case, the entropy is not complexity so much, it's kind of that freedom, or the lack of structure, the least amount of structure that the Q, which is the distribution of the states in the brain, measured this way. So without really getting hung up on the mathematical principles, we can think about energy minus entropy, but we'll also give it some other ways, because this math allows us to write this in at least two different ways, and I'll cover them in a second. But we have seen these equations, so the points I want to kind of emphasize and remind is that Q is some kind of approximation that the brain, as a modeling device, or in this case it could be also artificial brain, artificial neural network, this is what it can learn because of its capabilities, whatever it's built for. The true world maybe has slightly different structure. So we are either trying to match the errors between whatever are the underlying true causes in the world and what the brain can guess or learn. This aspect, which is the negative log probability, we call it surprise. So the brain avoids surprise, but also it tries to match the underlying hidden causes. So the whole idea here is that remain alive means some homeostasis or adaptation to the environment, which is done by avoiding surprising states, which means avoiding surprising observations. So we actually don't know the states, we know the observations, but we go with this logic. And this is done by minimizing the approximation to surprise using free energy, where the surprise itself comes from the environment, but this is the quality of our approximation. So I think a little bit more intuitive way, at least in my eyes, is if you think about this now, not as a concept, but really as one of the implementations. So in neural networks, there is this architecture or model called Variational autoencoder, which is actually pretty recent. I think it's not more than like 4 or 5 years, which was made a lot of impact on the ability of these deep neural networks to learn things. And it is a generative model, and I'll talk in a second what the generative means here. But the whole idea is that this is what it means, autoencoder. The way it's trained is basically you take some data, you plug it into this structure. I'll explain this in a second. And then you also regenerate the data, okay? And you basically try to see how well this network regenerates the data. Now, in the context of the brain is here somehow. These are the sensations, they come, and the brain does the analysis and finds these underlying causes. And there is a switch in notation here, which was always, I was kind of playing with two different articles. So here you see I have X and Z instead of S and O. But X are the observations, so X are the O's, and Z are the hidden states or the states, the S. Okay, so it's the same, exactly the same logic, just the letters changed. So you analyze, you find your latent or internal representation, and then you're basically going back and generating the data. So this is this path. Okay, we're going back. Now, here there is no question about what it means. You just basically plug in data and you have images here, you get images out, images in, images out, sounds in, sounds out, text, whatever. Okay, we don't ask ourselves if these generated images are hallucinations of the computer. I mean, they're rendered to us, okay? But in some other sense, it could be here, I don't really know to tell you what it means. It means that our imaginations, our kind of internal brain, higher brain functions, create sensations. How do we perceive them? Here, you have video camera in, screen out, okay? Microphone in, speakers out, okay? If you think about this as imagining, then great. So here's the process. And in this process, basically, the learning happens by training here the neural network, and the neural network is trained using this, what we call the loss function. So it tries to maximize. So it's trying to maximize this criteria. This criteria is called technically evidence lower bound. So for those who kind of might want to look into the neural network, again, this is as an example here. Again, this is not something that I expect or want anybody to start programming in this class. But I just kind of want to show this analogy because First of all, these are exactly the same equations, okay? This d and this k are just two different ways for the same function. This is the distortion, or so-called Kublik-Leibler measure, that measures the distance between, the model, the variational, the approximate states, and the true states of, so these are the hidden states, right? The S and the Z. And here is this thing, which is the expectation you average over all possible states S. And you also actually have to generate a lot of examples. This is why you also generate a lot of O's. You average on everything. And in Friston terms, in the brain, the free energy of the brain literature, this is sometimes called complexity, and this is accuracy. Now, why I'm bringing this example? Because I think it kind of helps to think about this process. If you don't think about this in our own consciousness terms, this is encoder and decoder. You encode the data into some internal representation, and then you decode it, okay? And you compare the error between your original input and the output, and you use this error to train the network. And that's how you learn. Now, again, it always kind of bothers me, well, so if this is also happening in the brain, what it means decoding is decoding means we dream these images or we dream these sounds. Does it happen when we are awake or asleep? So there are some algorithms that actually go through these two phases. In autoencoder, it's just encoder, decoder. Now, the other important part is that this is random states. This is randomness. So once you learn this, you can start generating more and more internal states, and they trigger data. So this has this ability to generate. This is why it's a generative model. It's not mapping this to fixed like grandmother's neuron. You show a grandmother this one will file. You show a grandfather another one will file. Fire. I mean, like activations. These are probabilities, okay? And that means it can constantly generate more and more and more latent states. And once you imagine, you take these latent states and they're rendered back to the actual surface, like the musical representation, the actual observation. So I think by now we've used so many times this idea of states and observations, or latent states and data, that I hope this kind of dichotomy is clear. So the point about this ability to generate is really crucial, and somehow also in neural network literature, again, I cannot repeat referring to this just because I know that some of you are probably going to look into this in some other occasions, or at least have heard about this and might be interested. Generative models are usually considered pretty late in, if you learn machine learning, you don't get to generative models as your initial or first class in machine learning or neural networks. But I think once you think about generative models, that's where it becomes interesting. That's where it becomes talking about imagination, talking about generative stuff. Before that, it's really just differentiable programming or optimizing functions. Really, it's just boring math in some sense. No, I mean, I don't want to say boring. I mean, I don't want to insult anybody. Interesting in different ways. So let's agree on some terms, first of all. So if we use this analogy of complexity and accuracy this time, so we kind of left this energy entropy. We can call this also as accuracy minus complexity minus accuracy. It really depends. They're all different ways of writing down the same goal of avoiding surprise by approximating it with another machine that can imagine, basically. So if we want to think about it this way, complexity indicates how much our approximation of the posterior, which means the hidden state. So latent state, hidden state is sometimes called posterior. Posterior in the sense that this is the inference, right? We find this, uh, uh, from the data we infer the posterior. So this is our approximation. How our approximation deviates from the prior, and the prior means the real world. So again, these are kind of very technical terms, but basically the QS deviates from PS. The internal world, the internal representation of the underlying causes that happen in the world deviates from the true, which we don't observe, only the observations. And then accuracy is actually looking into the observations. So how likely, okay, what we imagine about the causes are given that we observed something. Now, the generative model here is basically based on the idea that, first of all, the observations are distributed. This is a probability. And what we want to do is find a mapping so that we can infer the states from the observations. And inferring means we learn the distribution, we learn the probability, so that when we can randomly now draw internal state from whatever we learned, which means we can kind of imagine or trigger some imagination, we eventually can get back the original observation. Very mathematically said, but the whole idea of the generative is that everything is a probability and a probability, and we basically can generate random internal representations, and from these internal representations we go back and we get the actual images or the actual data. So the hidden states are randomly generated, so there is some kind of an underlying noise that drives just the fact that QFS is a probability. That means that there is something that generates these states all the time, and this ability of deriving the states from the observations is called representation learning. So the states become kind of a representation. We extract maybe, I don't know, these are images. We extract lines and angles, or parts of face, or maybe in sounds we capture certain like frequency combinations. Maybe we learn what are notes or harmonies. So we take the signal itself and we break it into some kind of an internal representation. Now, why it's important to be able then to regenerate? So this is actually the quote from Geoffrey Hinton, who was the first one kind of to point out that we need to have these generative models. He said that to recognize, you first learn to generate. Okay, that was kind of his, I would say, motto, but explanation of, or the motivation for using our generative models. And another thing is, well, you are able to imagine things, right? If I say imagine a pink unicorn, you can do that, although you have never seen a pink unicorn. So it's kind of related to the ability to generalize. And one of the things that we want an organism or a neural network to do is generalize, in the sense that we provide some examples, but then you want it to be able to kind of make sense of new data, right? You train it on, whatever pictures you have labeled in Facebook, and then it sees a different picture and can recognize the face. So this ability to recognize things outside of what it was trained on means generalization. So this is kind of the underlying motivation, the pink unicorn. So now the next step is actually introducing time, because so far we didn't talk about anything which is time related, but we're dealing with music. So the most natural way of doing this is thinking that there is an underlying time progress here, and the states of the world change over time. And then the brain also has to kind of track some dynamics, some structure in time of these inferred states. So not only you have some kind of internal representation in your mind, it also has its own dynamics. It progresses, okay? And of course, there are the observations. There is whatever you can actually sense. So it's kind of the same thing, except for we added this time dimensions here. Now, when the next state, so here is the index t is the time, when the next state, s of t, depends only on the previous state, which is t minus 1, this is called Markov property. So if you've heard about Markov chains, that was kind of the idea, that you have some kind of probability of the next event depending on the previous event. Of course, you can have not only one step back memory, you can have many steps back. So this is what's called variable Markov memory size. And music typically has variable Markov memory. Now, of course, in this notation, nobody said how long is this s and how long is this, how long is st and how long is st minus 1. But if you assume that they all represent fixed chunks of time, then maybe st needs to be also conditioned. Now, this notation means that this is given and this is what we predict. So you can predict time t given st minus 1, but maybe you need to have here st minus 2, minus 3. So this is kind of the variable memory size. And of course, chord progressions. You don't predict the next chord based on the previous chord alone. You depending on, of course, the specific musical situation, but you might consider 2 or 3 or 4 chords before that to be able to decide how to follow. And actually, in say if these are lychee kind of chord progressions, there's this concept of bricks that some people use in jazz, which are really like connections of blocks of progressions. And also, melodic motifs. You can have phrases, you can have motifs, you can have melodies, and and responses. So it's clear that the structure can have very different temporal kind of dependencies. But if we just assume this basic model, this becomes so-called hidden Markov model. And I guess some of you have heard about this concept. And hidden Markov models, existed way before deep neural networks or any kind of the new kind of brain-motivated machine learning. They basically could be understood also as some kind of a very simple game. And it's also used in speech and music, but before jumping there, let me just kind of explain hidden Markov model, mostly for the purpose of showing the most simple model that includes, latent states or hidden states and observations, where the latent states have their own dynamics. So the idea of hidden Markov model is something like you have different bowls with balls. So you have this urn, 1, 2, 3, and each one actually has the same, it has balls with same colors. I mean, they're all different colors, but all of the colors are in each of the balls. And so you can have blue and gray, green and red. The only difference is that their proportions are different. Okay, so this one seems to have more blue balls than this one, and I don't know, maybe this one has very little red, this one has more red. Now, why do we do this sort of a game? Well, the idea is that the observations are given, they're the visible. So you have a sequence of these balls, and you have 2 tasks to predict maybe what will be the next. So there is an underlying dynamics here, okay? So, and the dynamics here that there is some kind of a hidden hand. So these urns are behind the curtain, and there is a hand moving between here and here. You might draw a couple of balls here, and they can jump here. You can come back. You can maybe keep on going. But there is some sort of a underlying rule here that moves between these states in in random but not totally random way. There is a structure to the way you tend to jump. Maybe you stay a lot in this state, and then you just jump to this one, come back. But from this state, you can also go here, but you cannot almost, there is very little probability jumping from here to here. So there is this underlying structure here that you don't see. But every time this structure, when it arrives at each one of these urns, it randomly chooses a ball. And what you see is this sequence. And then your task is basically to tell which underlying state, by observing these balls, you have to guess, oh, I think here it was drawing balls from this urn, now it switched to maybe this one, then maybe it came back again here, and here it jumped here. Okay, so you have to kind of estimate these based on these observations, but this is very ambiguous. I mean, this red ball can belong here and here and here. So this is kind of the formal representations of all these hidden states observations. There are these transition probabilities, emission probabilities. I will not explain these beyond just providing it here, but let me show an example where this makes sense. So for instance, speech is very often modeled as hidden Markov model. And what are the hidden states? Hidden states will be our, phonemes, maybe diphones, okay? But these will be the phonetic expressions that underline basically the text. And what are the observations? The observations are the actual sound signal, okay? You can think about this also as music, and people were using the same HMM also for music, although it wasn't very common, but they're quite convincing examples. So what would be the hidden states? Maybe this would be kind of chords, notes, because if we observe music, these are like very complicated states. Most likely these are chords. I mean, actually you can do chord estimation with this, and that will be the next slide. But the whole idea is that this is the speech, this is kind of the text, or the phonetic, that these are the movements of your mouth, right? You move, this is what controls your phonemes, but eventually this is what you hear. And what you do is you observe these sound segments and you guess that this is a phoneme, and then maybe you stay in, because if this belongs to ah, so maybe it's ah, and you keep on staying here, and then you jump somewhere else, and then you stay there. I mean, in this case, this is kind of left to right. This is a typical model of speech, but in theory, you could go back and forth. So this is hidden, and in the case of text to speech or speech to text, this would be the text, and this would be the acoustic signal. Okay. So this is kind of one intuitive model where you have latent states and you have temporal dynamics. Chord estimation with HMM, that's another example. So the idea is basically to be able from the audio recording, here the audio is represented as something called the chromogram. I don't want to go into details, but it tells you basically how much energy is in frequency bands that correspond to the 12 notes. These are 12 notes. And you want to be able to estimate which chords these are, but you also want to kind of stay within a chord. You don't want to jump every state to different chords. There's this dynamics. You learn the logic of chord progressions. And this is kind of the typical model for combining. So here the concept really is that chord is a latent state in music. Now, another critical concept, which is really something that Friston, kind of articulated. I wouldn't say again that this is totally originally his idea, but he really articulates that, and this is less common in some of the previous work where you do just inference. He articulates the idea of action. And if you remember, I mean, the whole title of these slides was active inference, okay? but we never talked about what is active about this. Okay, you can say active in the sense that it does some prediction, but here there is actually more like agency. So the idea is that if you think about something that happens over time, you not only predict the next step, you might take some action that will change the environment. And this is very specific. This really applies either to robotic systems that operate on the world. It can also operate on systems that kind of actively seek the data, and saccadic eye movements in some sense are represented because you choose what you see. You can say something about attention also as being active, but you can think also about physically moving to a different location where your sensations will be different, okay? Or deciding that, if you're improvising, you do some movements, you do some action, okay, to change where the music will flow. So the action is important. So then I'll just mention this concept. We will not be looking into this too much, but choosing a sequence of actions is called policy. And active inference is sometimes called also epistemic foraging. Why? Because you don't know what will be the next state until you do the action. And you don't know what action to take to optimize your desire for least surprisal, right? So what it has to do, in these situations, you actually have to rehearse. You have to do a lot of exploration. You try different actions until you land at the best policies. So you kind of create your knowledge by foraging through different actions. You search the space of possible evolutions here. And then, policies that minimize free energy in the future are preferred. So you kind of go back to this concept of a free energy, but you include action in it. And this is really something that when Friston talked about his free energy principle, he actually added here a lot of additional mathematical symbols that, I don't want to go into. And there is a change in notation in a second, but let me just kind of look into these two different formulations that are, we have seen them over and over. And the idea is that there are external states in the world, there are sensations, there is internal states, but there's also an action that actually goes and changes the world. And the two representations that we saw, one was surprise with divergence, and one was complexity minus accuracy. Sorry. So yes. Mm-hmm.
Is the reason why then complexity minus accuracy is the form is that the same as Lagrangian sort of minimization? Because it reminded me of that.
Well, actually, free energy could be viewed as some kind of Lagrangian constraint where you basically, let's say, fixed, some, it depends what you decide being fixed, but if you say, you have some kind of a fixed energy, then you this becomes a constraint and you minimize on the entropy. So definitely, you can see this as a constraint optimization process here.
Is the other, would the other one be like a Hamiltonian?
Well, here the dynamics, when Friston writes things here, he assumes there is some dynamics here, but if you ask me how to derive this from like dynamical equations, he does that. I didn't go into that. Okay.
Okay.
I think on the level of just the concepts, and I think we can all relate just to these words, even though I'm kind of trying to warn everybody and say, let's try to be specific about them. But getting specific to the level of math is really not my purpose here. So we can think that he actually speaks about these two things. One is that the role of perception is to optimize, overall, this kind of a surprise. We said brain wants to minimize the surprise, and it tries to match the internal structure of the world by its own internal structure, and this is the divergence. So he claims that mu is some kind of a parameter on the internal structure of the brain, and brain tries to do that, but then it can also act on the world, and he can actually do action here, and the action appears in this part because the sensations now, these S are the sensations, and again, my apologies that the notation is inconsistent. Sensations are observations, so this is in our notation is O. These sensations depend on the actions, so you choose actively your sensations, but to be able to emphasize the aspect of the action, you need to look into this type of formulation. So even though they're equivalent, the actions operate on the sensations. They're here, and the internal representation is here. And he kind of uses this duality in the representations to claim that if you want to think what the brain can do, it can either adapt to the world or it can act on the world. And this is seen in this representation of complexity minus accuracy, while its perception or its inference is modeled by this divergence part. So slightly from a different article, and again slightly different presentation, but this is also Fristen's paper. So here's basically a common thread in both machine learning and the free energy principle approach, is that learning is related to minimizing free energy, where the free energy is some kind of a strange equation that could be written in all of these different forms. Okay, you can think about this as energy minus entropy, and it's written in a very specific way. Then you rewrite these probabilities and you get surprise and divergence. Okay, or you can write this in another way and get complexity and accuracy. So of course, once you start kind of getting very particular about meanings of these words in articles, kind of it's a pretty frustrating, or I don't know, just a bookkeeping exercise to go back and look up all these definitions. But for our purpose, I think if we kind of think about these two things, okay, that accuracy is something that you can act to match the perception to your expectations, while here the divergence is basically between your internal understanding of the world. This is where you learn, this is where you act, then you get these two representations, okay? And we have seen before that this is exactly what this variational autoencoder did, which is just one way of implementing this. And just the notations here are different, so I kind of try to write this down. So,
can I ask one quick
yes,
question?
Yes, of course.
So you're saying that definition of energy minus entropy is the same as is complexity minus accuracy?
I'm saying that these are different ways. I mean,
they're different ways of saying the same thing, kind of.
Well, there are three different formulations of the same principle. They mathematically are slightly different because energy is defined in a specific way, and the entropy is defined in a specific way if you want to go to the actual equations. But then you can play with the algebra inside, and you move parts of the probability to different representation, and you can get something else that you can call surprise, and something else that you call divergence, or something else that you call complexity, and something else that you call accuracy. Now the question is how particular or precise we need to be when we speak about these terms. I think not very much. I think the principle itself is really this trade-off between internal representation and how well we match the world. And then the main point from this set of slides is just that you can think about one of them being more suitable for action. So if you think, complexity minus accuracy, the accuracy is basically how your sensations are generated based on your internal states, and this is where you can input your action to change this. While in the surprise and divergence, so the surprise in some sense is the surprise on the evidence. You just get something, it's like more perception. You see something, you're surprised, you don't act on the surprise. Okay? So the surprise is more the perceptual part. And in this formulation, the divergence itself is on the internal states, is how your understanding of the world matches, the underlying causes in the real world. So this is more like the passive, this is more the perception part. While in the other formulation, you have the chance to insert also action. Okay. So I would say if you want to kind of memorize something about this, we could basically keep that in mind. Okay. That maybe accuracy has A in it, which means action. Again, we're using English as a very broad language, right? We assign terms and then we insist on them, but accuracy means also many other things, right? So we could kind of try to agree that in this context, this is what it means, because this kind of is pretty consistent across the the papers when they mean these things. So
Can I just, sorry,
yeah.
I can ask a question later.
No, you can ask now.
Actually, can you go back 2 slides? It's the one where we have like the perception at the slide. So
yeah. Mm-hmm.
I understand because you were talking about the action to minimize the surprise. That there's an option of taking action to minimize the surprise, so that you are also you're minimizing the surprise, but you're also trying to close that gap between the internal and the external. And my question is that if that is the arrow meant to be one way, or can it not also point the other way, because it's the action that is going to change the things that are happening to the perception?
So this is from his article. So he pointed this one way, but actually there's no reason why it wouldn't go both ways. I think when it goes this way, it more refers to action of your sensory. So it's like saccadic eye movement. Okay, it doesn't really act on this. It doesn't act on the environment, but it actively chooses your stimuli. So there's this also kind of another layer of I don't know, say complexity in the sense of dealing with reality, right? If you think about, there is one aspect of action is that you actually, even your perceptual organs are not totally passive. I don't know about the ear. I don't think on the level of the cochlea we can control which frequencies we hear, right? So that, like, if you listen to some things and you say, oh, I hear these notes and chords and the rest is noise, we usually think about this more cognitively. At least that's how I think about this, right? It's not perceptual. It's not that you don't hear it. You kind of don't attend to it cognitively. But apparently in eye movement, you don't really see the world. I mean, you have saccadic movements that scan the world. We're not aware of this, but I mean, the eye always moves. When you see an object, you actually scan it. So there is this aspect of action even in the perception, because the claim is that your saccadic movements, I mean, it's almost like what is the chicken, what is the egg? Are your saccadic movements done randomly just to get a picture of the world, or you imagine, you think that you're looking into a specific object, and then you guide your saccadic movements to trace the important parts in this object. So there is also this action. So in that case, your basically internal state guides the guides the action that influences, your sensations. But it's not that you change the world, you just actively were selecting your sensations. But
Okay.
if you actually change the world, then you can go both ways. Okay.
Okay. Thank you.
So in this case, actually, I did think more about agent operating on the environment. So the model comprises of internal sensory and active state of the organism versus external, which are also hidden states of the environment. Action maintains the function of the organism, its ability to classify or predict by minimize its entropy and entropy. So there is an article about autopoiesis that if somebody chooses to take, they kind of relates this question. And again, entropy and negentropy, we have to be careful there about what we're minimizing, what we're maximizing. So pardon me for not like actually defining why there is the neg here. And then internal states infer the hidden causes of the sensory state by maximizing this Bayesian model evidence through action. Okay, so kind of retelling the same story with now all of these super kind of formal mathematical terms, but I mean I hope it kind of makes sense now intuitively. And the summary is the organism tries to minimize the error between what it actually senses and what it predicts that will be sensed. And then, of course, okay, so this is something I mentioned before. Is the agent causing its own sensations? So are saccadic eye movements caused by stimuli of eye muscles? And is there something like auditory imagery that you basically imagine actively because that's what you want to hear?
Professor.
Yes.
One quick question about this saccadic eye movements, and I'm not sure if I'm either missing things, but does that occur at a local level? It's not like a higher cognitive processes are controlling that. It's sort of a local fine tuning, and does that play any role in this modeling? Because
I'm not an expert enough to tell you what actually happens in terms of what causes the saccadic movement. I think here the question was very much what you're asking. Are saccadic movements driven by higher brain functions?
Yes, I don't know anything about the saccadic eye movements. It's just
or are the saccadic movements kind of just autonomous, just scanning, right? If you think about like, I don't know, camera, at least when it was cathode ray tube, it would scan, right? It would go scanning like this. So it didn't go jump randomly to sample things, right? And pixels in the camera sample everything in a fixed way. But apparently our eye is very selective, and it seems to be following contours and from the images of saccadic eye movements superimposed on like objects. You see that you can tend to focus on important features of, let's say, a face. Now, why? Well, apparently you recognize it's a face, then you guide your eyes to look into points of the face. It couldn't be that it kind of randomly kind of goes and selects very specific points.
Yes, that's sort of what I'm.
Yeah, so I think that's the. So your question is also my question.
Yeah. Yes. It makes me think of like there's different parts of the brain that recognize different angles of our face, like the STS.
Right, but then apparently it guides the eye.
Yes.
To look into them. So your sensation is guided by your perception. If perception is kind of refers to a higher level, you guide your sensation to selectively choose things. So it could be that when you listen to, I don't know, Western tonal music, you guide your. Well, I don't think we can guide sensations of music. we selectively do some selection on the perceptual side, but apparently on the level of the eye, also your sensations are controlled.
I see.
But it's an interesting question. I don't know. I mean, and even that kind of, I think a lot of this is where we say that the sensation ends and perception starts and then cognition starts, right? So one other interesting example, which is sort of like counterintuitive, but it appears in several papers. Okay, it even appears mentioned in the Bayesian brain paper, and there is the paper about the Markov blankets that talks about this, and this is this sea squirt that eats its own brain. Okay, now I mean it's a fun video. I'll play it before we switch to the next set of slides. But I mean, why is it interesting, or why they bring this as an example? So I think the motivation here, or the enigma, is why would basically an organism that tries to adapt to the environment, right? In order to create this homeostasis, why does it go and basically reduce intentionally parts of its internal brain capacities, right? Why it kind of destroys part of its model, parts of its nervous systems, in order to fulfill this homeostasis. It's almost like going in the opposite direction. It takes action, but I think part of the question that I want to raise later on for discussion is, there is this idea that we selectively choose our sensations, or we do something to create a certain world that we want to see. And there is a claim that if you want to be a sea squirt and live the way it does, in order to live in the world of these actually living organisms that look like plants, they have to kind of regress almost to plant state to maintain this community growth and stay and operate as sea squirt. Because if it kept its abilities to move and swim, it wouldn't be eventually what it is. Now, it builds a very safe environment for itself. And once it reaches a certain point in its evolution, it basically, instead of evolving, it devolves. So I'll play this video and I'll leave this totally as an open question. But I think the other implications are maybe, first of all, this is an animal that lives in colonies. It's kind of a group situation. So maybe to allow the group to coexist, it actually needs to be kind of suppressed as its own individual abilities, because otherwise it will not create that environment that it wants to exist in. So let me just play this, and then I'll pause the recording, and if time permits, I'll jump to the next set of slides. And it should be playing. It's embedded. You have to press somewhere. Okay, if not, let me open this. Yeah, okay. So can you see this? I have this open on the tab. Okay.
Yeah, I can see.
Oh, I think oops. Sorry, I need to share again with sound. Where is that? Oh, I lost it. Here it is.
About sea squirts, speaking of the ocean.
Can you hear
Like
me?
sponges and corals, they
You
appear
can
to
hear
sit
it?
on the ocean
Yes.
floor all
Yeah.
day doing nothing, but they're actually, their difference actually ends, and they're actually more similar to us than you'd think. And they do some things that are pretty damn bizarre. For instance, did you know that sea squirts at a certain phase in their life cycle actually eat their own brain? For sure. If you want to know more, come on Ben's lab. Sea squirts. These cool little marine creatures are found in coastal waters all around the world, generally in warmer regions, often clinging to ship hulls and colonising new areas like weeds. So what are sea squirts? They are a group of sessile marine organisms known in scientific circles as tunicates. They belong to the animal group known as ascidians. They actually form somewhat of a bridging group between vertebrates like us and the more primitive invertebrates, and I'll show you more later on. Sea squirts and other marine invertebrates such as sponges are very different. From an unknown common ancestor, all life on Earth radiated, including bacteria and archaea, protozoans, plants, fungi and animals. Sea squirts belong to the animal group Chordata, which also includes animals such as frogs, horses and other vertebrates. As far back as 1866, biologists noted that all vertebrates share certain characteristics at a certain point in their lives as embryos. These characteristics are seen in human gill slits, a nerve cord and notochord, a stiffened rod, running along its back, the forerunner of our backbone. Sea squirt larvae display these characteristics too. It is the dorsal nerve cord and notochord which links them to us. The sea squirt larva is actually more complex than the adult, with complex organs including primitive eyes, a motile tail, and a cerebral ganglion, a very primitive brain. The larval stage is quite brief, sometimes after only a few hours after hatching. The larva finds a suitable place to put down roots, so to speak. The brain and other organs are absorbed by the larva as it undergoes metamorphosis, much like a caterpillar turning into a butterfly. Why eat its own brain? It no longer needs it. The adult is now essentially a pump, drawing in and filtering food particles from the seawater via muscular squeezing and the beating of hair-like projections called cilia. Food goes in this end, seen in blue, and comes out the other. Okay, so what is a sessile marine organism again? You may be asking yourselves that, so I'll explain it to you. Essentially, a sessile organism is one which, well, at some part of its life cycle will attach to a substrate. In the case of these sponges here, they've attached to this seaweed, and they're going to stay there for their entire life. You can see more of them here. See how they attach? Because sponges obviously don't move, so they spend their whole lives in one spot. Similar case with these corals here, which have started to grow on the stem of this seaweed here. And that's essentially all sessile is. It stays in the one spot its whole life. Sea squirts are quite hardy, colonising new areas readily. They have many fascinating properties, which make them of keen interest to science and medicine. They may even hold promise for anti-cancer therapies. I really hope you've enjoyed this episode. It's been fun making it. If you like learning and want to see more, subscribe.
Okay, so that's pretty much, that's the end of today's slide. So let me stop the recording and open this up for questions.